Hello and welcome. I will be your SQL coach. We have two main goals in this course. In Chapter 1, we will get to know databases, which store and organize data electronically. We'll discuss how databases and the data they store are structured. This context will prepare us for our second goal, to extract data from databases using SQL code in Chapter 2. Let's dive in. A database stores data. Let's imagine that we are in charge of storing and organizing data for a library. We might set up a database that holds information such as the data pictured here on patrons, books, and checkouts. This information is housed in objects called tables, with data organized into rows and columns. This database contains a patrons table, a books table, and a checkouts table. A closer look at the patrons table shows that it stores various data about our library's patrons, like library card number, name, the year the patron became a library member, and the total overdue fines the patron owes our library. A relational database defines relationships between tables of data inside the database. For example, each of our library patrons might each be associated with several checkouts. Through these relationships, we can draw conclusions about data housed in separate tables in the same database, and answer questions such as, which books did James check out during 2022, or which books are checked out most often. These tables might look similar to the way data is organized in spreadsheet applications such as Excel or Google Sheets, but databases are far more powerful than spreadsheets. Databases can store much more data, and storage is more secure due to encryption. Possibly the biggest advantage of a database is that many users can write queries to gather insights from the data at the same time. When a database is queried, the data stored inside the database does not change. Rather, the database information is accessed and presented according to instructions in the query. Which leads us to the star of this show, SQL. SQL, or SQL, is short for Structured Query Language. It is the most widely used programming language for creating, querying, and updating relational databases. Once we are familiar with the data we have and which table it is stored on, we can use SQL to begin writing queries to answer questions about our library. More on that in Chapter 2. Now that we know the basic organization of a database, let's take a closer look at the main building block of databases, tables. We saw in the previous lesson that databases are organized into tables, which hold related data about a particular subject. As we've seen, tables are organized into rows and columns. In the world of databases, rows are often referred to as records and columns as fields. A table's fields are limited to those set when the database was created, but the number of rows is unlimited. Let's talk a little bit more about table naming. Table names should be lowercase and should not include spaces. We use underscores in place of spaces. And ideally, a table name would refer to a collective group, like inventory, but it's also okay for the table to have a plural name, such as products. A record is a row in a table. It holds data on an individual observation. Taking a look at the patrons table, we see that the table has 4 records, one for each of the patrons. The record for Yasmin indicates that she became a member in 2022 and owes $2.05 in fines. A field is a column in a table. It holds one piece of information about all observations in the table. The name field in the patrons table lists all of the names of our library patrons. Because field names must be typed out when querying a database with SQL, field naming is important. Generally, field names should be lowercase and should not involve spaces. A field name should be singular rather than plural because it refers to the information contained in that field for a single record. This is why our table has card num and name fields rather than card nums and names. Similarly, two fields in a table cannot have the same name. Finally, field names should never share a name with the table they are housed in, so that it's clear in all cases whether a field or table is being referred to. A unique identifier, sometimes called a key, is just what it sounds like: a unique value which identifies a record so that it can be distinguished from other records in the same table. This value is very often a number. In the patrons table, it makes sense to use the card num field as the unique identifier for each patron, not the name field, because it's possible that as our little library grows, two patrons might have the same name. Having more tables, each with a clearly marked subject, is generally better than having fewer tables where information about multiple subjects is combined. Take a look at the patrons and checkouts tables. Now, here's what our patrons and checkouts tables would look like if we tried to combine them. It's the same data, but much less clear because it now contains duplicate information. While we can see that Izzy has 2 checkouts and Maham has none, the card num column is no longer unique because it is Izzy's multiple checkouts. We can always use SQL to gather information from multiple related tables and connect them if a question requires it, but table topics should remain separate. Welcome to the final part of the databases chapter. This lesson will focus on the data inside a database as well as its storage. When a table is created, a data type must be indicated for each field. The data type is chosen based on the type of data that the field will hold: a number, text, or a date, for example. We use data types for several reasons. First, different types of data are stored differently and take up different amounts of storage space. Second, some operations only apply to certain data types. It makes sense to multiply a number by another number, but it does not make sense to multiply text by other text, for example. In programming, a string refers to a sequence of characters such as letters or punctuation. On the patrons table, the data in the names field is made up of strings, such as Maham and James. SQL has several different data types that can hold strings. Some string data types can only hold short strings, such as a string up to 250 characters. Storing short strings in a small data type like this saves storage space. SQL's varchar data type is more flexible and can store small or large strings, up to tens of thousands of characters. Because of its flexibility, varchar is very commonly used for storing strings. Integer data types store whole numbers, such as the years in the member year column of the patrons table. Just as with strings, SQL offers a few different data types for storing integers, depending on how big the numbers we'd like to store are. Int, a common SQL integer data type, can store numbers from less than -2 billion to more than +2 billion. Float data types store numbers that include a fractional part, such as the $2.05 that one patron, Yasmin, owes in fines. Just as we might expect, SQL also offers several float data types depending on how many digits the numbers in the field are expected to be. The numeric data type can store floats which have up to 38 digits total, including those before and after the decimal point. Now that we're familiar with data types, we can look at a database schema. Schemas are often referred to as blueprints of databases. A schema shows a database's design, such as what tables are included in the database and any relationships between its tables. A schema also lets the reader know what data type each field can hold. The schema for our library database shows the varchar data type is used for strings like book title, author, and genre. We can also see that the patrons table is related to the checkouts table, but not the books table. Finally, let's discuss storage. The information we find in a database table is physically stored on the hard disk of a server. Servers are centralized computers that perform services via requests made over a network. In our case, the service performed is data access, but servers are also used to access websites or files stored on a server. Any computer can be a server if it is set up to provide a service, even a laptop. However, servers are generally very powerful and large machines because they are best equipped to handle a high volume of requests and data. Welcome back. Now that we understand how data is organized in databases, we can begin drawing insights using SQL queries. Recall from the last chapter that SQL is used to answer questions both within and across relational database tables. In the library database, we might use SQL to find which books James checked out from the library in 2022. In an HR database, we could query salaries for employees in marketing and accounting to determine whether pay across departments is comparable. In many organizations, SQL is used as a complement to other tools such as spreadsheet applications. If the data we're interested in can fit in a spreadsheet and does not have many relationships to other data of interest, we can analyze it in a spreadsheet. But for sprawling and diverse data, such as the data related to a retail platform, organizing the data in a database is best. Then, we use SQL queries to uncover trends in website traffic, customer reviews, and product sales. Which products had the highest sales last week? Which products get the worst review scores from customers? How did website traffic change when a feature was introduced? SQL shines when an organization has lots of data with complex relationships. Let's write our first SQL code. To do that, we will need to learn a few keywords. Keywords are reserved words used to indicate what operation we'd like our code to perform. The two most common keywords are select and from. Perhaps we'd like a list of every patron our library has. The select keyword indicates which fields should be selected. In this case, the name field. The from keyword indicates the table in which these fields are located. In this case, the patrons table. Let's put these parts together. Here's how the query should be written. The select statement appears first, followed on the next line by the from statement. It's best practice to end the query with a semicolon to indicate that the query is complete. We also capitalize keywords while keeping table and field names all lowercase. Now let's take a look at the results of our query, often called a result set. The result set lists all patron names, just as we had hoped. Note that we have not changed our database by writing this query. The tables, including the patrons table, are exactly the same as before we wrote the query. In order to share our results, we can save the SQL code we have written so that our collaborators can use it to query the database themselves. We'll cover saving queries in a later lesson. To select multiple fields, we can list multiple field names after the select keyword, separated by commas. For example, to select card number and name, we'd list both field names in the order we'd like them to appear in our result set. Notice that this does not have to match the order the fields are presented in the table. Listing name before card num means that name appears first in the results. As you might expect, we can select three fields, such as name, card num, and total fine, by listing all three field names after the select keyword and separating them with commas. What if we'd like to select all four fields in the patrons table? We could list out the four field names after the select statement, but there's an even easier way. We can tell SQL to select all fields using an asterisk in place of the four field names. It's time to level up on our SQL queries by learning a few more commonly used keywords. Let's dive in. Sometimes it can be helpful to rename columns in our result set, whether for clarity or brevity. We can do this using aliasing. Perhaps we'd like to select the name and hire year for each record in the employees table. We could alias the name column as first name in the query by adding the as keyword to indicate an alias of first name after selecting the name field. The result set now has first name rather than name as the column header. The alias only applies to the result of this particular query. In other words, the field name in the employees table itself is still name rather than first name. Some SQL questions require a way to return a list of unique values. Let's imagine that we are interested in getting a list of years in which we hired our current employees. If we select the year hired field from the employees table, the result set shows several years listed twice, which isn't what we are looking for. To get a list of years with no repeat values, we can add the distinct keyword before the year hired field name in the select statement. Now, we can see that all of our employees were hired in just 4 different years. It's possible to return the unique combinations of multiple field values by listing multiple fields after the distinct keyword. Take a look at the employees table. Perhaps we'd like to know the years that different departments hired employees. We could use this SQL query to look at this information, selecting the Dept ID and year hired from the employees table. Looking at the results, we see that Department 3 hired 2 employees in 2021. To avoid repeating this information, we could add the distinct keyword before the fields to select. Notice that the department ID and year hired fields still have repeat values individually, but none of the records are the same. They are all unique combinations of the 2 fields. Finally, let's discuss saving SQL result sets. In SQL, a view refers to a table that is the result of a saved SQL select statement. Views are considered virtual tables, which means that the data a view contains is not generally stored in the database. Rather, it is the query code that is stored for future use. A benefit of this is that whenever the view is accessed, it automatically updates the query results to account for any updates to the underlying database. To create a view, we'll add a line of code before the select statement, create view, then the name we'd like for the new view, then the as keyword to assign the results of the query to the new view name. Here, we create a view called employee hire years by assigning the results of a query selecting 3 fields from the employees table to a new view. There is no result set when creating a view. Once a view is created, however, we can query it just as we would a normal table by selecting from the view. Our last topic in this short course is SQL flavors. SQL has a few different versions or flavors. Some are free, while others have customer support and are made to complement major databases such as Microsoft's SQL Server or Oracle database, which are used by many companies. All SQL flavors are used with table-based relational databases like the ones you've seen, and the vast majority of keywords are shared between them. In fact, all SQL flavors must follow universal standards set by the International Organization for Standards and the American National Standards Institute. Only additional features on top of these standards result in different SQL flavors. Let's take a look at 2 of the most popular SQL flavors. PostgreSQL is a free and open-source relational database system which was originally created at the University of California, Berkeley, and was sponsored by America's famous Defense Advanced Research Projects Agency, or DARPA. DARPA also sponsored research leading to creating the Internet, the computer mouse, and GPS. The name PostgreSQL is used to refer to both the database system itself as well as the SQL flavor used with it. SQL Server is also a relational database system that comes in both free and enterprise versions. It was created by Microsoft, so it pairs well with other Microsoft products. T-SQL is Microsoft's proprietary flavor of SQL used with SQL Server databases. Think of SQL flavors as dialects of the same language. If Claudia speaks American English, she will have no trouble understanding people on a trip to London, even though most people in London speak British English and there are some small differences. Here's an example of a small difference between SQL Server and PostgreSQL. When we want to limit the number of records returned, we use the limit keyword in PostgreSQL. Here, we limit the number of employee names and IDs selected to only the first two records. The exact thing results are achieved in SQL Server using the top keyword instead of limit. Notice that this keyword is the only difference between the two queries. Limiting results is useful when testing code, since many result sets can have thousands of results. It's best to write and test code using just a few results before removing the limit for the final query. New SQL learners may wonder which flavor they should learn. This may be an easy decision if a learner knows that her employer uses Microsoft's SQL Server, for example. Or it might be a hard one for a job seeker or student who doesn't know what database management system a future employer might use. Don't worry too much about what flavor to learn. As we've seen, the differences are small. A PostgreSQL wizard can become a SQL Server wizard by learning a handful of different keywords.